Hello everyone, my name is Parthasarathy and I'm here representing my co-authors in presenting our ASPLOS paper, Warehouse Scale Video Acceleration, Co-Design and Deployment in the Wild. Our work is motivated by two key observations. First, the growing importance of video workloads. Video today is the dominant form of internet traffic, accounting for more than 2/3 of internet traffic. Video processing also underpins important applications in education, business, collaboration, entertainment, etc. The recent pandemic has only accelerated and amplified the adoption of video processing even further. In addition, the computing demand for video processing only continues to grow. Higher resolution like 4K, 8K, but also newer applications like augmented reality, virtual reality, cloud video gaming, IoT video, etc. While all this growth is happening on the demand side, on the supply side, improvements from Moore's law have stalled. We are now in the era of custom silicon and domain-specific accelerators, but there's relatively been very little work on data center video acceleration, with most prior work limited to simpler consumer video acceleration. So in summary, this is the problem that our paper seeks to address. How do we address these challenges of exploding demand but slowing supply for video processing? Specifically, how do we design new video accelerator systems optimized for warehouse scale and cloud use cases? Addressing this problem, our paper makes three main contributions. First, we present key insights on how warehouse scale video processing is fundamentally different from consumer use cases. Specifically, we identify unique challenges and opportunities relating to workload and data diversity and higher quality requirements, but also new constraints around throughput and availability at scale and co-design with warehouse scale software stacks. Second, leveraging these insights, we present the design of a new video acceleration system co-designed across hardware and software. We introduce the VCU, the Video Coding Unit, a new domain-specific accelerator that implements the computationally expensive parts of video processing, while at the same time carefully architecting the right abstractions and partitioning to work in large distributed systems and with warehouse scale scheduling software. We discuss the design of our scheduler, as well as the use of high-level synthesis for agile hardware development. Finally, we present detailed data and insights from our experience deploying the system at Google over several years. Specifically, we present both benchmark and fleet-wide data that shows the effectiveness of our domain-specific acceleration. More than an order of magnitude performance per TCO, performance per cost, over prior well-tuned software implementations, all while maintaining stringent data center quality and availability requirements. But perhaps equally important, we also discuss how our accelerator system enables new capabilities that were otherwise not possible across a range of workloads, from video sharing to photos and video archival to live streaming and cloud gaming. So let's jump right in. I'd like to introduce Jeff Callow to start by discussing how video processing at warehouse scale poses unique challenges and opportunities for new accelerator design. Jeff?
Thanks, Partha. In the easy old days of classic TV broadcasting, there was a single video format and a single resolution for all devices supported. Today, we watch video on a large range of devices like desktops, flip phones, smartphones, and TVs supporting 4K and 8K resolutions. Therefore, YouTube converts a single input video into up to 9 different output resolutions. The different file sizes of these are used to adapt to a viewer's network conditions to deliver the highest supportable resolution. More outputs are needed for higher frame rate and 12-bit high dynamic range, so an 8K 60 FPS HDR input can end up generating 24 different outputs. But wait, there's more. Video coding specifications define how to convert a compressed video sequence back into pictures. Popular ones include H.264, VP9, and AV1. The first VCU encodes H.264 and VP9, so we could generate up to 48 outputs per video. A future VCU with AV1 would mean generating up to 72 outputs. Producing multiple outputs per input video is a key difference between a video sharing service and a consumer video application like video chat. This complex conversion to multiple resolutions and formats is called transcoding and must operate at a massive scale. 500 hours of video is uploaded to YouTube every minute, with a similar volume of video also being uploaded to Google Photos and Google Drive. Also, instead of generating a single output per worker, or SOT, we can be more efficient by decoding once and generating all these outputs to one worker. We call this multi-output transcoding, or MOT. Diving quickly into the encoding process, after the input is decoded, the encoder reads the raw frame, performs pre-processing like downscaling, and uses a rate distortion algorithm to do a computationally expensive multidimensional search for motion and optimal predictive tools both within and between frames. The results are entropy coded for further compression. Newer coding specifications have higher compression, but also increase search space by adding more prediction tools. Another dimension is the diversity of workload and usage patterns. The processing system is used for all Google products with this video, each with varying needs and latency storage playback trade-offs. We have the time to spend more effort compressing YouTube uploads than YouTube live streams. Photos and Drive videos are watched less than YouTube, so storage concerns have more weight than keeping up with the newest coding standard. Upload volumes vary from the massive YouTube level down to the tiny Google Books. Finally, video popularity follows a power law, with head videos being very popular and worth spending a lot of resources to compress more, the body being somewhat popular and worth spending a moderate amount of resources, and the long tail, which needs broadcast quality but using fewer resources. Finally, there is an existing warehouse-scale computer context bringing its own requirements for cost at scale and resilience. Cost savings are gained as area under the curve, so time to market and agility are also considered. In summary, creating warehouse-scale computing accelerators for video workloads is fundamentally different than doing consumer video hardware. We need new ground-up designs targeted at this environment, which Clint Smolin will talk about next.
Jeff just talked about the requirements for warehouse-scale video processing, but we feel the three principles shown here are generally applicable to all warehouse-scale accelerators. Following these principles require planning for workload diversity and churn, optimizing for both high performance and quality, and balancing cluster-level availability with individual component reliability. We utilized hardware-software co-design to push complexity to the appropriate level, leading us to ossify as little as possible, allowing firmware and software to adapt to changing requirements. I'll now walk through the system design and some of the decisions we made. Starting at the lowest level, our encode block is related to prior mobile encoders, but we spend more area to enable higher quality, improved compression, and to adapt it for data center use. Error detection provides visibility into hardware issues, and the extra area allows for up to 3 reference frames, improved motion estimation, and the evaluation of more RDO candidates. At the ASIC level, efficiently transcoding large MOTs requires many encoder and decoder cores all in a single chip. We chose 4 channels of LPDDR4 with sideband ECC to provide the required bandwidth, and mostly use error correction throughout the rest of the chip to enable reliable operation. The floor plan at the top right shows that most of our area goes to the encoder cores, with the DRAM subsystem being the second largest. Not all transcodes can saturate a chip by themselves, so we use isolated, firmware-managed queues to allow concurrent transcodes. Each system has 10 boards with 2 VCUs each, as shown on the left. We maximize the VCU density per system to improve performance per TCO dollar while avoiding bottlenecks in the host system and network. A caveat is on CPU decoding, which improves utilization in decode-limited scenarios, but can itself cause PCI Express bottlenecks. VCU hardware errors do not usually impact the system, as each ASIC is operated by a separate job. At the cluster level, we offload non-transcode processing to the non-VCU machines, and VCUs are deployed globally to enable processing close to where videos are uploaded. While this was just an overview of the bottom-to-top system design, we hope this highlights some of the ways that warehouse-scale computing motivates significantly different design choices. Jeremy Dorfman will now talk about the software and firmware that enables this at-scale system.
Thank you, Clint. Our video processing system maintains a number of logical worker pools with VCU or CPU transcoding resources. As transcoding requests enter the system, work is scheduled onto a pool based on use case and priority. Each of these pools has its own scheduler, which assigns work items to workers based on an estimation of the resource requirements for a work item and based on the availability of resources in the pool. These resource dimensions are flexible. Sometimes they map to physical resources like codec cores and DRAM. Other times they map to some hard-to-attribute metric like PCI Express bandwidth. The scheduler is implemented as a sharded in-memory table of workers to resources. Workers periodically update the scheduler with their available resources, and the scheduler sends work items to workers based on that availability. The scheduler seeks to maximize load on workers because as workers become idle, they can be released from a logical pool for use by other pools. In the event of a failure during transcoding, work is rescheduled within a logical pool, either onto another VCU or CPU. Broadly speaking, video coding on the VCU keeps persistent stream state in per application VCU DRAM, and the codec cores are activated to perform some command and update that state on completion. Our codec cores typically have a per frame granularity. For example, an operation could be encode this frame to some VP9 bit stream. The firmware is responsible for multiplexing processes onto a VCU. Each application has a command queue and response queue in memory shared with the VCU. As applications write commands into their command queues, the firmware schedules between queues and activates codec cores with the commands. It's only at the application where the codec-specific programming happens. The firmware is oblivious to the contents of the commands. This programming changes often, and so it doesn't make sense to ossify it into silicon or even run it in the firmware. And this loose coupling allows for our typical data center cadence of multiple software rollouts per week. This has enabled us to improve our encoding efficiency, starting pre-silicon and continuing through the lifetime of the VCU. We used high-level synthesis for the encoder's design. It's been our experience that HLS is much more efficient to design with. Our tooling consists of Mentor Graphics Catapult and an in-house integration tool called TAFL. Catapult is used for HLS to RTL synthesis, and TAFL is used to glue the HLS together, both pre-synthesis as a C model and post-synthesis as an RTL design. Our use of HLS allowed for novel use of the LLVM sanitizers, especially address sanitizer and memory sanitizer, to uncover issues where the hardware would have misbehaved or had some undefined behavior. Because our C model was available throughout the project's development, we were able to use our video quality corpus of many thousands of videos, along with many thousands of servers, to identify and fix a number of perceptual quality issues pre-silicon. Perhaps most importantly, HLS's agility made evaluating and implementing encoding tools much faster compared to a conventional HDL design. Notably, we were able to add a few very late features that would have otherwise been prohibitive. HLS has been critical to reconciling the tension between YouTube's changing needs and the relatively long lead time of ASICs. Clint and I discussed the design and implementation of VCUs in the data center. Please let me introduce Marissa Bell Guevara, who will discuss the results of this deployment.
Now we'll take a look at the performance of VCU, both on micro benchmarks and fleet-wide data running production workloads over a long period of time. Offloading video encoding to custom silicon provides up to 100 times more throughput than software encoding. To compare the efficiency of VCU to prior platforms, we use the metric performance per total cost of ownership, where TCO includes capital and operational costs associated with each platform. VCU provides a 7x improvement in perf TCO for H.264 encoding relative to the software baseline. And for VP9, the perf TCO uplift is 33 times higher. This data accentuates the value of hardware acceleration for new generations of video coding standards, where the compute load has greatly increased to provide higher compression efficiency. VCU has given us a breakthrough in compute capacity at scale, which has enabled several new capabilities across multiple products. One example is multi-output transcoding, which was previously prohibitive, especially for VP9, due to the high latency of running MOT workers at scale. In fact, our production workload is largely MOT. Running MOT instead of single output transcodes is a big win. MOT throughput is 30% higher because a single decode is reused multiple times to produce all the output resolutions. The figure shows measured throughput per MOT and SOT production worker. The lack of variability seen in the MOT trendline also illustrates that we are able to utilize the encoder cores close to maximum capacity. The evaluation of a video encoder must also consider the encoding quality. With VCU, we are serving broadcast quality video for several Google products. The following data shows that the encoding quality of VCU is comparable to software encoders. We use rate distortion curves to visualize the perceptual quality measured in peak signal-to-noise ratio and compression efficiency of software and VCU. RD curves are effective visualizations of the nature of lossy video encoding. Encoders may represent a video using more or fewer bits, shown on the horizontal axis, to achieve higher or lower perceptual quality, measured by PSNR on the vertical axis. The points on the curves are formed by encoding the video at different bitrate targets. As you can see, VCU VP9 on the right-hand side achieves similar perceptual quality at similar bitrate as the libVPX software baseline on the left-hand side. We do this comparison for all the videos in the vBench suite, which is a public set of YouTube videos that demonstrates the diversity and encoding complexity of the content that is uploaded to video sharing services. Across the suite, VCU provides encoding quality that is comparable to the software baseline. Hardware-software co-design has been key to enable post-deployment improvements that have real impact to the end-user experience and the usability of VCU in a warehouse environment. This graph shows how we improved the encoding quality of VCU with bitrate on the vertical axis steadily dropping over time by tuning the rate control algorithms that are guiding the encoder. The software baselines are also constantly improving. Hence, a first-order design goal for VCU has been this ability to parameterize the encoder so that a year after it has been deployed, we have a better version of VCU that is just as good as the software. Hardware-software co-design also gave us the right knobs to tune the workload via scheduling. The figure on the left-hand side shows total VCU throughput increasing over time as we migrated software transcoding to the VCU workers and as we rolled out performance improvements. One example can be seen on the right-hand side, where the utilization of the hardware decoder was at 98%, in fact stranding valuable hardware encoder capacity. Leveraging our multidimensional bin packing mechanism for load balancing, we shifted some of the decode load to the host CPU, bringing down the hardware decoder utilization to 91% and further boosting encode throughput. Hardware-software co-design also led to a more resilient VCU system, where we have the ability to disable individual devices rather than a full system in the presence of failures. I'll hand it over to Danner Stodolski to close and set the stage for future work for VCU and the community. Thank you.
Thanks, Marissa Bell. This paper's work on warehouse-scale video transcoding builds on top of several areas of prior research. In particular, there is a rich literature on hardware blocks for partial or full acceleration of video encoding or decoding, primarily focused on mobile environments, as well as particularly challenging algorithmic blocks. Also noteworthy is work on ASIC clouds, which explored hardware acceleration of a number of workloads in data center environments, focusing on the complex trade-offs between operating cost, unit cost, and the substantial one-time expenses involved in ASIC fabrication. Hardware-software co-design of data center accelerators for video rendering and machine learning has significant literature as well. Many of these workloads involve tightly synchronized compute farms. In contrast, the workload in this paper is much more loosely coupled. Finally, there is a large literature on warehouse-scale scheduling focused on balancing the throughput and latency requirements of diverse workloads under the constraints of data center topology, compute resources, and second-order effects such as cross-workload interference. This literature is mostly focused on CPU, not accelerator scheduling. Right. To conclude, this paper presents the rational design and experience with a warehouse-scale accelerated video coding system. This infrastructure is designed from first principles to meet the cost, quality, and fault tolerance requirements of Google, where over 500 hours per minute of video, as well as tens of thousands of concurrent live streams, are transcoded into a large variety of formats, supporting products such as YouTube, Google Photos, Meet, Stadia, and many others. This paper describes the system choices from ASIC design to system packaging to scheduling that mesh together to deliver a continuously available planetary scale broadcast quality video system with an order of magnitude improvement in cost performance. We also highlight key aspects of the system design that supported both pre and post silicon tuning and evolution. The work opens up further avenues for research in large-scale video and related accelerator systems. Large-scale systems of this sort require a village, and I'd like to acknowledge the significant contribution of all the VCU authors as well as numerous Google teams into making it a reality. Thank you.